And so, again, the job that we've been trying to accomplish is you give me some kind of mathematical description of a linear time invariant system. In our case, it's been a difference equation, a particular kind of difference equation, a linear constant coefficient difference equation. Then I need some kind of description of an input signal, whether that's a bunch of sample values or a closed form analytical expression, some function of n that tells me what all those sample values are for any n. And I also need to know what are the initial conditions on our system. Is it working off any previous inputs that it still hasn't finished responding to that will become part of the total solution of the system? With that information, then we need to try to predict what will the output of the system be. And again, depending on the form that we get the input described in, that will probably determine what form we can describe the output in. We've talked about two methods so far for system analysis. We've talked about doing it numerically by recursion with a recursion table, where we take sample values of the input signal combined with a difference equation to then come up with sample values of the output signal. Our first analytical method was solving a difference equation, taking the system description difference equation and solving it for the particular input and particular set of initial conditions to come up with a closed form analytical solution, a function of n that describes the output signal from the time that we impose the new input, which we usually regard as n equals 0 from that time forward. And we were accomplishing that by splitting up the problem into solving the 0 state response and the 0 input response. Our next method that we're going to address is convolution. And convolution relies on us having a linear time invariant system so that we can apply the principles of linearity and shift invariance in order to come up with the total output of the system given an input system description. And we can do that in convolution. We'll actually be able to do it both ways. We can do it numerically like we did with the recursion table using a convolution table, or we can do it analytically with a closed form solution. In order to do convolution, though, we need a different system descriptor. For the recursion and solving the difference equation, we used the difference equation as our way of describing the system, how it was going to respond to any given input. For convolution, though, we're going to change what we use to describe the system to the unit sample response, which we'll derive from the difference equation, but it will take the difference equation's place in representing for us and giving us the information we need to know about how the system responds to given inputs. So we want to do that next week. We want to start addressing convolution, but in order to do that, we need this missing piece. We need to know, how do we get the unit sample response for a system that's described by a particular difference equation? And that's the problem we're going to tackle today. Given a difference equation, how do we derive what the unit sample response will be for that system? And again, the reason we want to do this is that we developed this idea of how we could use linearity to come up with a general form for the output of the system for any given input, assuming that I could describe my input as a sum of weighted and shifted unit sample sequences. Then if I know how the system responds to a unit sample sequence, that I can predict its output for any input by simply scaling and shifting the unit sample response by the same values that we're scaling and shifting the unit sample sequence in the description of the input. And that restatement of linearity and shift invariance is actually the convolution sum for discrete time systems. It is the operation of discrete convolution. Before we can apply this, though, I need to know, what is this unit sample sequence? What is this h of n? How do I get that in order so that I could put it into this summation equation and come up with a general way of finding a new output for any given input? And so that h of n then does become our system descriptor. It takes the place of the difference equation. It's derived from the difference equation. It contains all the same information, dynamic information, that the difference equation does, just in a different form. And again, we define the unit sample sequence as simply how the system's going to respond if it starts off relaxed, again, meaning all of its initial conditions are 0. The output is 0 for n equals -1, -2, however many samples we need for the given order of the system. So it's completely depleted. Any previous inputs and the responses to any previous inputs are all gone. We have a relaxed system, and we're now going to excite it at index n equals 0 with a single unity magnitude sample, a 1, 1 at n equals 0. That's our unit sample sequence that we use a delta sub n to describe. And we're going to have the response of the system to that simple input is going to be what we call h of n, the unit sample response. Now, how are we going to get that? Well, we've already actually done a few of these numerically. Conceptually, what we want to do is find an output of our system using whatever methods we have for that, and we have a couple so far. Using the difference equation as our system descriptor and predicting what is the output going to do when I put in a unit sample sequence and assuming that all of our initial conditions are 0. So can set up the problem that way, see what we get for an answer, and whatever we get out is what we call the unit sample response. So we've done this with recursion already. If we wanted numerical sample values of the unit sample sequence, we can certainly do that. We're also going to want to have it analytically. We're going to want to have some function of n that describes the unit sample sequence for any n. That's our goal now. We want to go up beyond what we were able to do previously with recursion and actually get an analytical function. And we'll have to do that by solving the difference equation. Although, because we have a relaxed system, it's going to be a simpler, fewer steps in our process here because I don't have to worry about a 0 input response. We're assuming all initial conditions are 0. We're going to set them all equal to 0 and find just the response to a new unit sample input, which would be technically a 0 state response. So I don't have to worry about the 0 input response piece of it. Okay. If we start off with a non-recursive system and see what the unit sample response is, that we've gotten by recursion before. And this was an example we tried a week or so ago. Said the output y of n was 2x sub n plus 5x sub n minus 1 minus 3x sub n minus 2. No y of n minus anything terms, so there's no feedback, no recursion. And we want to know, how is this system going to respond when we put in a unit sample sequence, 1, 1 at n equals 0? And we assume all of our initial conditions are 0, the system relaxed. And whatever comes out, whatever we determine, that is, in fact, by definition, the unit sample response h of n. So if you look back through your notes, we've done this recursion before. We have our 3 terms, x sub n minus 1, x sub n minus 2, and our computation of the output, which in this case will be the sample values of the unit sample response. And we can plug in the appropriate values for the input for a single unit sample sequence of x sub n. Has 1, 1 at n equals 0. X sub n minus 1 then is a delayed unit sample sequence, so that one occurs at n equals 1. X sub n minus 2 is a 2-sample delayed unit sample sequence, so we add a 1 here at n equals 2. And then we can simply read across the row for each index, plug in the appropriate values in the difference equation, and got the unit sample response, starting with initial conditions of 0, the system relaxed. And the values we got out when we did this were 2, followed by 5, followed by minus 3, and then everything after that was zeros. So this was the answers, the sample values of h of n that the recursion table gave us. And it turns out we commented that it appeared to be true, and it actually turns out to be true, that the unit sample response of any non-recursive system has a finite length. There's only a finite number of non-zero samples in the unit sample response, and then it goes to 0. Therefore, we called these non-recursive systems FIR, finite impulse response systems, because they had this characteristic that the h of n did go to 0 after some finite number of non-zero samples. And every non-recursive system has that behavior. An FIR system, at least a non-recursive system, we can always find the unit sample response very easily directly from the difference equation. Because as we saw from the recursion example, for a given non-recursive difference equation, as we apply a unit sample to that, we can actually just rewrite this equation with our definition of a unit sample sequence. Unit sample response. The unit sample response h of n is just y of n when we replace x sub n with delta sub n's and make sure all the initial conditions are 0. So if we literally make that substitution in our equation, we see that h of n replacing y of n, replace x sub n with delta sub n, replace x sub n minus 1 with delta sub n minus 1, and so on. We get a closed form expression with a few unit samples, sequences, or unit samples of the unit sample response. H of n is 2 delta sub n plus 5 delta sub n minus 1 minus 3 delta sub n minus 2. Or its sample values were 2, 5, and minus 3, and all the rest were zeros. Now you've noticed, I hope, that these sample values for the unit sample sequence, or the coefficients for these unit samples in the analytical expression, are nothing other than the B coefficients from the difference equation. The B0 coefficient, the B1, and the B2 coefficient are in fact the sample values of the non-zero samples of the unit sample sequence for a non-recursive system. And it will always be that way. So you give me a difference equation, I know immediately the sample values of the unit sample response. I can write them out in longhand form, or I can give them to you as samples. Very simple, very straightforward. Just kind of a nice feature of non-recursive systems. Recursive systems, not quite so easy. Here we have the one that we have worked through a few examples on. Y of n is 1 x sub n plus 1 x sub n minus 1 minus 1 half y of n minus 1. Here's our recursive term. We have a feedback. It's a first order recursive system. And if we tried to do the same kind of substitution to come up with a closed form solution for what is h of n, replace y of n with h of n and x of n with delta sub n, doesn't work out quite so well for us. Now, we found the answers by recursion, and again, we did this example previously. It's a little more complicated how we do the recursion when we have the feedback term, when we have a recursive system, because not only do we have our x sub n's and delayed versions of x of n, which would look the same as they were in the previous example, putting in a single delta sub n sequence puts 1, 1 for x sub n at n equals 0. The x sub n minus 1 term then gets this one delayed one sample. But now we have to have the previous output sample value to feed into the equation for the computation of the difference equation value. And so there we need to know what an initial condition is prior to n equals 0, which again we assume a relaxed system, so that it has to be 0. And prior to that as well, so that also tells us what any initial condition values we need are. We feed those forward to the next row, so we can compute that unit sample response value. And going across, we would, for n equals 0, find that we have 1 times 1 plus 1 times 0 minus 1 half times 0, or just 1. And going forward, feeding that down here, computing the next value, feeding that down to the next y, and so on, and continuing to do that, we see a pattern emerge where the unit sample sequence is getting smaller each time. Its sign is changing each term. It's going back and forth, so it's kind of oscillating, getting smaller, but it's never going to get to 0. So if I wanted to truly specify the unit sample sequence with a recursion table, I would need an infinitely long recursion table. I'd have to keep on going forever. It looks like it settles down to 0, but if we looked on a much finer scale, we would see it's still bouncing back and forth, getting smaller and smaller and closer to 0 as we go out. And so this kind of recursive system is what we call an IIR system, infinite impulse response, because literally its unit sample response never quite gets back to 0. Whether it oscillates or not doesn't matter. It may be decaying, but it's never quite getting to zero. And most, not every, but pretty much all, well, all's too many, not all, but most recursive systems are IIR systems. There are a few exceptions. There are a few recursive systems, and we can actually deliberately design some feedback recursive systems that have finite impulse responses. But for the most part, they generally are primarily IIR, infinite impulse response systems. Okay, so we can use recursion. That works fine to give us the sample values for a non-recursive system that has a finite impulse response. For an IIR system, it'll give us values, sample values, but it certainly doesn't give us a function of n that describes h of n. Now we could try to do like the one homework problem and say, well, here's a sequence of numbers. Can I look at that, stare at it long enough and figure out, well, is there some functional formula I can come up with? No, this is cutting in half every time. So it's being multiplied by 1/2 and -1. So maybe it's some kind of -1/2 to the n function, but I'm not quite sure. We would have to try to infer it from the sample values. I'd much rather have a way to actually get an analytical expression out of the mathematics so I'm not guessing and checking here. So recursion is fine for sample values, not so useful for IIR systems, and certainly not going to get me a closed form analytical solution. That's really what we want, a closed form, some function of n that tells me what h of n is for any values. And it turns out for that particular system, and we'll derive this in a moment, this is the unit sample response as a function of n. It is some kind of -1/2 to the n, but it has a couple of terms to it, which may not be obvious from just looking at the numeric values. Now I'd like to arrive at this starting at the difference equation. And I can't get here like I can with the FIR systems, the non-recursive systems, where all I have to do is make that simple substitution. Let y of n be h of n, let x of n be delta sub n, because, well, begins looking promising. My h of n equals, replace x sub n with delta sub n, x sub n minus 1 with delta sub n minus 1, and so on. But when I get to the recursive terms, the feedback terms, those aren't deltas. They're not x's, they're y's. So I have to call those h's. And so what I end up with is h of n in terms of itself, or at least a delayed version of itself, which is a recursive style equation. Now we've used the term recursion 3 different ways now. So hopefully it's clear what we're talking about. This is a recursive equation because I'm specifying h of n in terms of basically itself. And while there are ways to solve that kind of problem, they're not really straightforward. We need a better way to make the jump from a difference equation to this analytical closed form version of the function of n that describes our h of n. So how do we do that? Well, if we need a unit sample response and we have a general difference equation, which maybe is recursive, maybe is a higher order system. It may not be a single input case. It may be a general case equation, depending on how many terms we have on the right side. If all you need is numeric values, simple. We just use a recursion table, plug in the unit sample sequence, see what we get out, and everything's fine. And for FIR systems, that's sometimes often sufficient. If we want analytical closed form expressions for h of n, then if it's a recursive system, we're going to have to go in and solve the difference equation. So we're going to have to use the techniques that we've been learning over the last 2 sessions to actually solve the difference equation for that input with no initial conditions, so the system is relaxed. And when we try to accomplish that, we run into a problem that are going to lead us to requiring an alternative input model. Let me see if I can demonstrate for you what the basic challenge, the problem that we're going to have here is. Let's take that one example. That was y of n plus 1/2 y of n minus 1 equals x sub n plus x sub n minus 1. If we were going to address this and we wanted to know what is the output, what is y of n when the input x sub n is a unit sample sequence and all initial conditions are 0. So right off the bat, it seems like we've simplified the process a little bit, because number one, normally we would go after the 0 input response, but in this case, the 0 input response is going to be 0 because we have a relaxed system. We have all those initial conditions are 0. So we don't have to worry about 0 input responses, which is kind of nice. And if we want to go after the 0 state response, well, first we have to demote our equation to a single input case, which we can do that pretty easily. Y of n plus 1/2 y of n minus 1 equals x of n. No problem there. My problem comes in when I try to go in the next step, which is, let's go find the forced response of the single input case. This thing we called yf of n. To do that, we look at what is our input. And not what is our input right where it turns on, but let's go down a little ways. Let's look down a few samples and see what our value of our input is. And so we can look up that functional form in our forced response table. And for n greater than 0, x sub n, our input signal, has a value of 0. Which if we look up in our table, well, we don't have an entry for that. And really, if the input is 0, then the forced response is also 0. So we get a little bit nervous about that. But okay, I guess that's okay. I guess that's acceptable. Then we go after the natural response of the system for the single input case. And this thing we called yn2 of n, the natural response piece, that was we need to know what form the natural response is. Well, so we've already done this problem. We know the characteristic equation was a z plus 1/2 equals 0. So z equals minus 1/2. So our natural response, looking that up, is some unknown k times minus 1/2 to the n. And then we solve for k using an initial condition for a 0 state response, which is y of minus 1 has to be 0. And we plug that into our equation, k times minus 1/2 to the minus 1, which is minus 2 times k. That has to be equal to 0. The only way that's true is if k equals 0, and then our 0 state response for the single input case, then we need to start solving this to find the general case unit sample response. So that's the unit sample response for the single input case equals, well, no forced response and no natural response. There's our problem. If we use our standard method for solving this difference equation, I will always get 0 for the unit sample response of the single input case. So our basic process isn't going to work for us. It's not sufficient to do this. I've got to make some change to it to accommodate this input. And the problem is that my input went away. It has 1, 1 at n equals 0, and then it's 0 from then on. And it's not continuing to drive my system, so I don't have any forced response. So what do we do about that? What is this alternate input model that's going to make this work for us? So if you have a general linear constant coefficient difference equation, and you want to find the unit sample response by solving this equation, we still got to go through the process of demoting it to a single input case. So first we're going to find the unit sample response for the single input case. We'll call that h sub 0 of n. And again, that's the output of the zero state response for the single input case. There is no zero input response. And so if we do our substitution, even though it gives us a recursive equation, for the single input case, we'd have h0 of n plus a1 h0 of n minus 1 plus however many terms we have for the y side. Because it's a single input case, the only thing on the right side is x of n, which in this case is a unit sample. That's still a true statement. The way we find the zero state response for that is through one manipulation of how we solve these problems. Instead of solving it the way I just tried, with x of n being a unit sample sequence and figuring out what the forced response of that, which is 0, with all initial conditions equal to 0, instead, we'll let x of n be 0, like it is for all n greater than 0, and we'll use a special initial condition to drive our answer, to provide the equivalent stimulus to the system so that we can see what it would do with that unit sample input. Namely, we set the output at index n equals 0, which is the value of our single input case unit sample response at n equals 0. We set that equal to 1. Use that as the initial condition that we use to solve for unknown coefficients. And if we have more unknown coefficients, well, we still keep the system relaxed. So h of minus 1, h of minus 2, however many we need, are still 0 for the single input case. And that's how we make our method for solving difference equations still work for this unit sample sequence. Now, that's a little fishy. That seems a little odd to just declare, let's just do it this way. Let's set h of 0 equal to 1 and magic happens. Well, it's provable pretty easily why that would work, why that would be. And it comes back here into our single input case version of the unit sample response equation, the difference equation. If this is true, we rewrite it in the output equals a collection of inputs and previous outputs form, like we were computing it in a recursion table. So take all the h terms that are output terms, y terms, back over to the side of the equation. So we have an equation for how I compute the current value, h of n, of the unit sample response for the single input case. So again, the only thing I have left over from the original right side of the equation is x of n, which is now just a delta sub n sequence. Let's evaluate this equation at n equals 0 to see what we're supposed to get. So h0 of 0, we get a delta of 0, which is our 1 unit sample. And if the system was relaxed and causal, all the previous outputs and all the previous unit sample response values have to be 0. So h0 of n minus 1 has to be 0, h0 of n minus 2 has to be 0, all of them. And so all those terms go away. And I'm left with the condition that I was proposing to use for our solution, h0 of 0, the single input case version of the unit sample response, has to always be 0. No matter what the difference equation is, this will happen. So we'll use that in our solution. So we find a unit sample response for the single input case equation. That's, again, just as when we were solving difference equations, that's not the answer I'm looking for. I want the answer for the general equation. So how do we take the single input case response and make it the general response? Well, the unit sample response is a zero state response. And so we use the same method to generalize the single input case unit sample response and make it the unit sample response of the general case. Any operations that are shown on the right side of the equation, if we multiply x sub n by b0, we'll multiply the single input case unit sample response by the same b0. If we take x and delay it by 1 and multiply it by b1, we'll take h0 of n and delay it by 1 and multiply it by b1, and so on. We'll apply linearity and shift invariance to our single input case response to make it the response of the general system. So let's try an example. Let's back up on the one we started. Same difference equation. Let's try it now with this corrected method and see how it plays out differently. So still true that the zero input response is zero because the system is relaxed. We'll still work with first the single input case, which is that y of n plus 1/2 y of n minus 1 equals just x of n. And it's still true that the forced response is 0 because x of n equals 0 for n greater than 0. So we still won't incorporate a forced response. So our whole 0 state response for the single input case, which in this case has only a natural response piece because the forced response was 0. And this is the thing we're going to call H0 of n, the single input case unit sample response. Has the form based on our difference equation, has a form of the natural response, some unknown k times 1/2 to the n. And now we use our special initial condition that is H0 of n equals 0 has to be 1. And we get k times minus 1/2 to the n equals 0, so to the 0, which is just k. So k must be 1. And we have our H0 of n then is 1 times minus 1/2 to the n, and that's for n greater than 0. So we'll put our u of n in there. And I got a solution. I got an answer other than 0. So that's a bit more promising. Now we're not done. That's the unit sample response for our single input case. We want the unit sample response for the general case equation. So let's go back up here. And let's observe what goes on this side. So we have x of n on this side, which is going to give us this H0 of n. So the unit sample response for the general case is going to have an H0 of n coming from this x of n term, and this x of n minus 1 term is going to give us an H0 of n minus 1. So I'm generalizing it just like it was any kind of 0 state response. And that happens to be a minus 1/2 to the n u of n. I have to replace all n's in my single input case unit sample response with n minus 1. So we would be adding a minus 1/2 to the n minus 1 u of n minus 1. And there's our general case unit sample response. So the process is all the same as what it is for solving any difference equation, except we don't have a 0 input response because the system's relaxed. That's our assumption. And for this finding the single input case unit sample response, we use a different initial condition. We use this special one that h of 0 equals 1. If I have a higher order system, then I'll use other initial conditions, but those will use the standard initial conditions. H of minus 1 equals 0, h of minus 2 equals 0, and so on for the single input case. For that particular problem, if we plotted out that h of n sequence, it'd be 1, then 1/2, and minus 1/4, then plus 1/8, and so on, bouncing back and forth again, decaying off towards 0. If we had a second order system, let's see how that changes the process. Actually, the basic method is the same. We just have an additional initial condition to worry about. Here's a second order system. I recognize it's second order because I have a y of n minus 2 in here. And let's find out what is the unit sample response of this system. So our new problem that we're trying to attack is a second order system. And I'm going to write it in the standard form. So we have all the y's on one side y of n minus 3/4, y of n minus 1, minus 1/4, y of n minus 2, there's my second order system, equals 2x of n minus 3x of n minus 1. So it's a general case equation and a second order equation. And if we wanted to find the unit sample response, then first we'll go right to the single input case, which is solving the simpler equation, y of n minus 3/4, y of n minus 1 minus 1/4, y of n minus 2 equals just x of n, the single input case. We know we won't have a forced response, so I'm going to need a natural response. So let's go get the characteristic equation, which in this case is 1 minus 3/4 z to the minus 1 minus 1/4 z to the minus 2 equals 0, or z squared minus 3/4 z minus 1/4 equals 0. If we factor that, that turns out to be z minus 1 times z plus 1/4. So I have two roots. Z is either plus 1 or minus 1/4. Two real distinct roots. And so our H0 of n, which has just a natural response, is going to be some unknown k1 times the first root, 1 to the n, and some k2 times the second root, minus 1/4 to the n. And we want to solve with our special initial condition, H0 of 0 equals 1. So we plug in n equals 0, we get k1 times 1 to the 0th power, n equals 0, plus k2 times minus 1/4 to the 0 power, which is just k1 plus k2. They have to be equal to 1 according to our special initial condition. I need a second equation because I have two unknowns. And for that, we use a standard initial condition, h of minus 1 equals 0. And so k1 times 1 to the minus 1 plus k2 times minus 1/4 to the minus 1, plugging back into the h0 of n, which is just k1 minus 4k2 equals 0. So now I have two equations, two unknowns. Turns out that k1 is plus 4/5 and k2 is plus 1/5. So we find that our H0 of n, this single input case unit sample response, is 4/5 times 1 to the n u of n plus 1/5 times minus 1/4 to the n u of n. And 1 to the n is just 1, so we can even get rid of that, which makes our general case h of n is, according to this, 2 times the single input case version minus 3 times a delayed version of the single input case version. So we would simply multiply that through 2 times 4/5 u of n plus 1/5 times minus 1/4 to the n u of n minus 3 times the same thing delayed, 4/5 u of n minus 1 plus 1/5 minus 1/4 to the n minus 1 u of n minus 1. And we could do the algebra and spread that out if we want, but that's the complete solution. So same process. Again, we just use our special initial condition. If I need more initial conditions, we use standard ones. we assume the system is relaxed, that we're finding a zero state response, so we set all the other initial conditions equal to 0. Here's what that looks like. That unit sample response bounces down, or kind of sinks in and actually settles in at about -4/5 or -0.8, and bounces around similar to that. Quick review of other things we can learn from the unit sample response. We can tell if a system is stable or not from the unit sample response. We said a system is BIBO, bounded input, bounded output, stable. If I put a bounded input in, meaning my x sub n's absolute value has an upper bound, and if I put any bounded input in, the output has to be similarly bounded. Could be by a different boundary, but it has to be finite, basically. We have a way already to tell that from the unit sample response. It turns out we can also tell whether a system is stable or not. Now that we know how to solve difference equations, and now that we know what a characteristic equation is, we can use the difference equation to tell us if a system is stable or not. The way we tell with the difference equation is find the characteristic equation, look at the roots, and every root has to have a magnitude that's less than 1, meaning all the roots of the characteristic equation have to be fractional values. They can be positive or negative, but they have to have a magnitude less than 1. That's because that's going to constrain the natural response to the thing we're exponentiating to a number that's going to decay rather than grow. For example, if this was the characteristic equation of our system, z squared plus z plus a quarter equals 0, that has 2 roots, that's repeated roots at z equals -1/4. That's a stable system. Its natural response is going to be -1/4 of the n plus n times -1/4 of the n, and those will be converging functions. If this was our characteristic equation, z squared plus 2z minus 8, that has roots of +4 and +2 and -4. That's not going to be stable. These roots have magnitudes that are greater than 1. And if we looked at what the form the natural response would take, it would be a 2 to the n and a -4 to the n. Well, that's 2, 4, 8, 16, 32. That's taking off exponentially. The problem we just did, even the single input case, if we look at that, for the problem we did that had roots of 1 and -1/4, that was not a stable system. It has that 1 to the n in it, which seems like it's all right, but by our definition, it's not. And if we look at that, its impulse response, its unit sample response levels off at a constant. This is the single input case version of it, by the way. And so that's not diverging. That looks okay. So we might think that maybe that 1 root is okay. The problem with that is if we actually found the step response of the system, the step response would take off. It would become a ramp function. And so strictly speaking, the roots of the characteristic equation all have to be less than 1 in their magnitudes to be stable. We already had another criterion based on the unit sample response for stability. We said the unit sample response had to be absolutely summable. We had to get a finite sum when we added up all the values of the unit sample sequence, which meant for FIR filters, they always were stable because we'd have a finite sum. For recursive and IIR systems, well, if we look at this one it has a constant output for the unit sample response, but if I sum this up as n goes to infinity, I'm going to keep adding 4/5 and adding another 4/5 and adding another 4/5 and adding another on infinitum. This has a sum of h of n that's infinity. So this is, again, for that definition, not a stable system. This system that we had solved that's recursive had natural responses and unit sample responses that had 1/2 to the n u of n's and delayed 1/2 to the n u of n's in the natural response. This is absolutely summable, right? If we look at the sample values of h of n, the characteristic of one that's going to be stable is it's going to tend to be converging towards 0. If we tried to find the sum of this, well, it's a little tricky, but if we find the sum of these absolute values, these are going to alternate back and forth. One of them is always going to be positive. One of them is always going to be negative. So each term is going to be something less than something getting smaller and smaller and smaller. But we can absolutely say that the magnitude of the sum of these has to be smaller than the magnitude of the first plus the magnitude of the second. And if we take those series and use our series formulas to see what these series sum to, they're both finite series. And so we get a finite sum. So, so both from the roots of the characteristic equation and the summability of the unit sample response would tell us that this system is stable. Lastly, we say that we can tell a system's causal by looking at the unit sample response. The unit sample response of a causal system has to be 0 for all n less than 0, because that then says that the system doesn't start responding until the input arrives, right? If a unit sample response is the response to a unit sample at n equals 0, if I have any response prior to that, I'm responding before my input happened, and I have a non-causal system. Okay, that's what we needed to get through to set us up for next week. That's the end of this segment and chapter. The homework number 3, then that's the last problems will be assigned around that to work on over the weekend. If you need extra help, please feel free to send me an email. But that's going to set us up for next week, where we're going to start using the unit sample response in order to start computing convolution integrals, or excuse me, convolution sums, to do system analysis by a new technique. And the good news for us in discrete time systems is, number one, convolution makes a whole lot more sense in the discrete time realm, and the mathematics are easy. It's sums, not integrals. We'll attack that next week.